Hi guys, today we're going to look at the integrating factor method as well as using Taylor series to help solve differential equations. So what we've learned so far is separation of variables and how to solve a homogeneous differential equation using like a substitution. Um, Basically, when solving differential equations, you have like a bunch of tricks that you try to pull out, and it usually depends on the form that it's in, right? Like for it to be homogeneous, it had to have the y over x, like a function of y over x. Uh, Same with integrating factor method. We're still working with a differential equation. If we notice that it has this form, then we would be thinking, let me use the integrating factor method, right? Always you should see if you can separate the variables first, but typically when it's in this form, you will not be able to separate the variables. And typically, like again, we wouldn't really write it like this. Like usually when we're writing it, we'd probably have something more like this, where it'd be q of x, you maybe have like p of x times y. And so all this is saying is like you might have some function of x, so like x squared, whatever. And this doesn't have to be a minus or a plus, so they just like plus some other function of x and times y, right? And so if it's like this, it's really difficult to separate the variables because it's kind of like what we saw before is you can't really just, multiply by 1 over y because you have to multiply this by 1 over y as well. And so the y is like stuck in there and it doesn't really help get rid of it. And so this is the other form you might see it in, where it's very difficult to separate the variables. And the key here is like, okay, I can see it as like a function of x here, and then it's a function of x times y here, not y squared, not y to the third, but just y, right? This will kind of go through the proof with you. I'm not going to do that because it's not really necessary to know like the whole proof. What we need to know is that we have this thing called the integrating factor, which is e to the integral of p of x dx, where remember p of x is this thing that's next to the y value, right? And here's some steps we can follow. So first thing we need to do is calculate the integrating factor. So recognize and calculate it. You don't need the constant integration. And then multiply it. So let's look at an example and go through this, right? So our example is going to be, I'm going to do the one out of the book because I don't have another good one to go over right now. And my pen's starting to go wacky again, so I might actually just have to pause this. So this is our differential equation. Notice you can see it's in this form where it's like dy dx plus some p of x, right? So our p of x in this case is the 3x squared times y equals some other function of x, q of x on this side, right? And again, it might be rearranged, so it might not always be this obvious, right? So first thing we do is calculate the integrating factor method, right? So in this case, integrating factor, in this case, it's I of x equals e to the integral of 3x squared dx, right? So we're integrating 3x squared. So in this case, it's going to be e to the x to the third over 3x to the third over 3, which is x to the third. This is our integrating factor, right? So we've calculated that. Next thing is we're going to multiply the differential equation throughout by I of x. We're going to take this and we're going to multiply throughout our entire equation here. So let me write our equation that we started with. And we're going to go ahead and take our integrating factor and multiply everywhere by the integrating factor. Right? And so that's what we did there, right? Next is simplify the left-hand side and hence obtain I of x equals integral of I of x times q of x d of x c, right? So we're trying to simplify this left-hand side. Hold on. Okay, and then since we didn't go through the proof, you want to look at this, and what I want you to notice is how this whole left-hand side is basically the derivative with respect to x of e to the ex to the third times y, right? And this will always happen. It will always be your integrating factor times y. It'll always be derivative of your integrating factor times y. But notice how it is, right? First, you'd have to use product rule, right? So you'd do derivative of y, which is dy dx, times e to the x to the third, which is this, plus derivative of e to the x to the third, which is 3x squared times ex to the third times y, right? So this whole thing here is just the derivative of ex to the third times y. And we know that that's still equal to this side, right? That's the way I had over on that side. So what that means is if I integrate this side, if I integrate both sides, I know that this side would just become ex to the third times y, because integrals and derivatives are inverses. And then that just means I have to integrate this side with respect to x, right? So I'm trying to integrate, I'm going to put the, no, come on, pen. Maybe I'll put the 6x squared out front. Right, and if we integrate this side, maybe you can see, maybe we need to use a u substitution, or you can just see it. But if u is x to the third, then du is 3x squared dx, and dx is du over 3x squared. Therefore, this would turn into 6x squared times e to the u. Dx is du over 3x squared, right? So these x squareds cancel, the 3 cancel a little bit, and you're left with 2 e to the u du, which the integral of e to the u is just e to the u, so you end up with 2 e to the u, which I'm going to go ahead and replace u with x to the third, plus c, right? And so we have ex to the third times y, e raised to x to the third power times, it looks like the y is an exponent, times y, equals 2 ex to the third plus c. We could solve for y, and we're going to get y equals 2 plus c over ex to the third, which is the same as what they're going to get over here, except they're going to rewrite that as a negative x to the third, bringing it up to the exponent. And so the real tricky piece of this is this step right here, right? Just recognizing you don't actually have to recognize anything. All you have to know is if you do this correctly, then whatever with this left-hand side will always be just whatever your I of x is. It will always be the derivative of whatever your I of x is times y, right? It will always happen. And then, you know, your other side is whatever, and you integrate both sides. Okay, so let's look at, and remember this is a general solution, right? We need some initial conditions for a particular solution, which they don't give in this one. Let's look at the next one, right? This one's going to give us a particular solution. I'm going to go ahead and write it over here and take you step by step through it. Okay, so it looks like this right now. If we're going to use the integrating factor method, it needs to look like, where to go, like this, where it's dy dx plus some function of x times y, and then it's equal to some function of x, right? So first of all, I need my dy dx by itself, so I'm going to divide everything by cosine x. That's going to give me dy dx equals y sine x over cosine x, that's tangent x times y, and then plus sine 2x over cosine x, and those you can't turn into tangent because this one has a 2 in it, right? And again, the way we want this is we want the piece with the y on the left-hand side, right? So we're going to go to move the piece with the y, which is this guy, to the left-hand side. So that's going to look like this. This is going to be a minus. Okay, so it's now in that form. You know, a function of x times y, and this whole thing's a function of x over here. So then we need to calculate our integrating factor, right? Our integrating factor is e to the integral of p of x, right? And remember, p of x is the piece that's next to y. So we're going to get that piece that's next to y, right? In this case, the piece next to y is, and this should be a plus sign, right? So it's going to be negative tangent. So it's where I of x is going to be, actually let me do this on the side. This will be side work, right? So I of x equals e integral p of x, which in this case is e integral negative tangent x, right? So we got to remember in this respect to x, what is the integral of tangent x? I don't know if our formula book gives us that, but they're getting e natural log cosine of x. So I can show you over here how to do that. Let's put the negative on the outside. Tangent, remember, is sine over cosine. If we use this substitution of u equals cosine x, then du would be negative sine x dx, and dx would be du over negative sine x. So if you replace that in here, you get integral, negative integral sine x, cosine was u, dx is du over negative sine x, and you'll notice that the sine cancels the sine, this negative cancels that negative, and you end up with the integral of 1 over u du, which is equal to natural log u, and remember then u was cosine x, right? So really this is going to end up being e to the cosine x. That's our integrating factor. Okay, we take that and we multiply it everywhere. So right, so it's going to be e cosine x dy dx plus e cosine x. I will put the negative over here because we're multiplying by tangent. Tan x times y, and that's equal to e cosine x times sine 2x over cosine x. Right, let's just make sure we're on track with what they have here. Yeah, and then oh, I see why. That's, yeah, sorry. It's this was natural log cosine. My apologies. Natural log cosine. Natural log cosine is what we had, right? I just messed this up, and then these cancel, so it's not e cosine x, just cosine x, right? So I'm going to get rid of that e everywhere, right? And then that's why these cancel, and you're left with, remember, tangent is sine over cosine, so here you're going to have cosine x dy dx minus, this is just going to be sine x times y equals sine 2x. Don't do this, computer. Sine 2x, right? And then remember, this side is always just the derivative. If you did this right, the derivative of I of x times y. Remember, I of x was cosine x times y. Right? You don't have to actually work it out, but you could try. If I take the derivative of this, I should get this, which check it. And then that's going to equal sine 2x, which means if I integrate both sides, I would get over here, the integral cancels this, and you're left with cosine x times y. If I integrate sine of 2x, I get negative cosine of 2x over 2 plus c. Right? Let's just check to make sure that's right. Yep. And then we're trying to solve for y, so I'm going to divide both sides by y, by cosine x, and I'll get negative cosine 2x. Let's put the 1/2 over here, over cosine x plus c over cosine x, right? Divide everything by cosine x, which then we want the initial condition. I'll let them do the initial condition. You're just plugging in the initial condition 0, 1, right? So if you plug in 1 is going to go in for the y, 0 goes in for cosine, and you get c equals 3/2, right? So then this value here would just be 3/2. And you would get something similar if you just rearrange it. All right, so that's that. There's 2 problems here for you to try using integrating factor method. And next we're going to talk about how to use Taylor series to do these. Okay, so I don't know if you remember, like you should remember, we were defining functions as using a Taylor or Maclaurin series, which is the Taylor series centered at 0, as a function of their derivatives. This is a Maclaurin series, right? Plus the second derivative evaluated, this is, yeah, Maclaurin series. The second derivative evaluated 0, x squared, plus in general, right, that you evaluate the nth derivative at 0 over n factorial times x to the n. And you could actually write a function, or you could approximate a function using this, right? What we're trying to do is we're starting with this, right? We're given the derivative, and we're trying to write the function, right? So like what we're going to do is, like, if I'm given, like, this is the only piece I don't know is f of 0, but all the times you're given that starting condition, right? If I'm given this, then I can write this, like pretend it's 1, and then I can evaluate the differential equation as 0, and I can put that here, right? So then I could write, that second term based on the differential equation. And it's typically easier to take derivatives than it is to integrate, right? So I could integrate and find the second derivative, or sorry, I could differentiate and find the second derivative and the third derivative and the fourth derivative. And then I would end up having this Taylor polynomial that approximate this differential equation, as long as I have, as long as I can take the derivative and evaluate it at that given point. So that's basically what all this says, right? When we're starting with some, given value. It's easiest to see this with an example. So we're gonna look at this one. I think this one's actually separable, so you probably wouldn't use this method on it, because you could just factor out x and then divide both sides by y, but divide both sides by 1 minus 4y. And you'd probably be able to solve it, but we'll check to see if it actually gives us the same solution. So we're given this dy dx equals x minus 4xy, and we know that y of 0 equals 1, right? So just imagine if I was writing this Taylor polynomial, I would know that the first term, this is going to be a Maclaurin polynomial because we're centering it at 0, right? The first term would be 1. The next term would be the derivative evaluated at this point, which in this case, the derivative evaluated at 0, 1, right? Because that's where we want this, is 0, 1, would be evaluating our function, which is this guy, at 0, 1, right? So the derivative gives us, if I plug in 0 for x, everything's just going to be 0. Right, and so this next term would just be 0 times x over 1 factorial. And then I would need to know the second derivative, right? So I just try to find what is d squared y over dx squared. And so that involves taking the derivative of this. They rewrote it, and they went ahead and factored out your x, so it's x times 1 minus 4y. And then you can use product rule. So the second derivative of x is 1 times 1 minus 4y, plus the derivative of 1 minus 4y is negative 4y prime times x. This is dy dx, right? Times x. And so you have that, and then you would, we can continue trying to find derivatives. So the third derivative would just be taking the derivative of this, which the derivative, if I distribute this 1 and these just go away, derivative of that is just negative 4 dy dx. Derivative of this requires product rule. So again, we're just going to look at this, u v. Derivative of u is negative 4 times the second derivative times x, plus derivative of x is just 1, plus minus, let's make this a minus because of that 4. Basically, it just turns into 4 dy dx. And then, again, the fourth derivative would be taking the derivative of this, which if I take the derivative of this, I get negative 4 times the second derivative. This one requires chain rule. So again, will be u v, and that would be, I guess we could clean this up a little bit first, right? Like I could actually put this with this, and that would be negative 8, which just makes this negative 8. And then we don't have to take the derivative of this guy, which is derivative of u is negative 4 times the third derivative times x, plus derivative of x is 1 times that. And then again, this would combine with this, and you'd get negative 12 dy minus 4, right? And that's the fourth derivative. And then the fifth derivative, you'd keep going and going and going. The idea would then be we actually need to know what these things are evaluated at 0, 1, right? So you'd be plugging in 0, 1 into these values, right? So here you'd plug in 0, 1. There's x is 0, this is 1. So this whole thing would go away. And you'd be 1 minus 4 is negative 3. So here we'd have negative 3 over 2 factorial times x squared. That's the second derivative, right? Third derivative, we're plugging in 0, 1. Notice there, so 0 goes here. This whole thing goes away. There's nowhere to plug in a 1 for x, but we know that dy dx evaluated at 0, 1 was 0. So this is basically 0 and 0. So the next term would be plus 0x to the third over 3 factorial. And then the next one is negative 8 times the second derivative. The second derivative is negative 3. So this is negative 8 times negative 3, which is 24. The first derivative, the third derivative was 0. This whole piece is 0. And so the next one is 24, right? So this is 24 x to the fourth over 4 factorial. And if we plug in, we have our, that was at that e, no, I did that wrong. Oh, I do have to do this one. And then 24 times, this would be negative 4 times negative 3, which is 12. So 24 plus 12 is 36. So this is 36 here. And then you could continue doing this. It's not easy, right? It's a pain in the butt taking the derivatives, but it's, I guess it's not that bad. You could keep doing this, but basically this is the polynomial that then approximate f of x, which is what we wanted to approximate, right? So again, you can see their work written out a little bit nicer. I was just trying to explain it. You can see how we get this polynomial factor, which if you simplify it, you get this, right? You're simplifying, you're just doing what is 2 factorial? That's 2, right? And then 4 factorial is 4 times 3 times 2, and it simplifies, and you end up with this. So that's the Maclaurin polynomial for our function. B was saying, I think, solve it exactly using separation of variables. So again, they're just going to go through separation of variables and give you this. And, you know, you end up with, if you actually get the final solution, you get this, right? You get y equals 1/4 1 plus 3 over 2 x e 2x squared, which is, yeah, it's just there, which you should be able to relate to this one up here somehow. All right, so that's the idea. Is just you're just basically creating a Maclaurin polynomial, or Taylor if they want you centered somewhere else, using the derivatives and the initial condition. Let's see. Maybe I'll do. Maybe I'll do 4 in a different video if you get stuck. How about that? No, change my mind. I'm going to do 2, so show you another example how to do that, and then hopefully we'll do 3 and 4 and 1 based on what I do for 2. Okay.